Scientists are tracking a unique visitor from distant space. Astronomers say the interstellar comet they've named 3I Atlas.
We've got some fresh images of 3I Atlas, a third ever interstellar object observed from Earth.
The surprising announcement from the Chinese space science community that they had released fresh, high-resolution images of the interstellar visitor known as 3I Atlas comes at a time when several major Western observatories appear to be significantly reduced in activity, or in some cases entirely offline. The images captured by China's advanced telescope arrays show the object with dramatic clarity, its coma and faint tail rendered with precision, while in parallel many traditional Western optical facilities are described as struggling to keep up, sidetracked, or even entirely going dark, for reasons still under discussion. Before we start, smash the like and subscribe buttons for more updates. From the very first detection of 3I Atlas by the Asteroid Terrestrial Impact Last Alert System Atlas survey, the object has fascinated astronomers. Its hyperbolic trajectory, its speed relative to the Sun and planets, and its display of comet-like activity have been flagged as signatures of an interstellar origin. The Chinese contribution deepens the mystery. Their imaging reveals unexpected structural features in the dust gas envelope and tail region that Western observations haven't yet matched in detail. With Western telescopes reportedly constrained by scheduling, maintenance, weather, or other operational hurdles, the Chinese release sets a stage shift in how interstellar objects might be studied. The Chinese images show 3Y Atlas with a crisp coma structure, asymmetric brightness distribution, and possible jet or plume features directed away from the Sun. These details suggest active sublimation and ejection of material, but also hint at more complex dynamics than offered by earlier Earth-based observatories. The clarity of the images implies that Chinese instrumentation, calibration, and data processing pipelines are reaching a maturity that can compete on a global stage. Meanwhile, the timing is notable. Many Western facilities are described as going dark, either because of instrument upgrades, lack of observation time, or simply the object's path moving into less accessible sky sectors. In effect, the Chinese images fill a gap at a critical moment. This shift in observational leadership carries broad implications. First, it underscores the reality that space science is increasingly international and multipolar. No longer is the Western Observatory Network the sole vanguard of discovery. Second, for this specific object, the early capture of detailed structure means the window of opportunity may be narrowing. 3. I-Atlas is moving rapidly, changing phase and geometry, and its visibility from Earth is evolving. A gap in Western observations could mean missing important transitional features before they fade or become inaccessible. Third, the event raises questions about how data sharing, coordination, and global access to transient phenomena are managed. If one nation releases advanced imagery while others are offline, the global science community must ask how to integrate, scrutinize, and build upon that data. The nature of 3I Atlas itself deepens the stakes. As a third confirmed interstellar object following 1I/Oumuamua and 2I/Borisov, it holds promise for helping answer fundamental questions about planetary system formation, the prevalence of interstellar visitors, and the composition of material originating outside our solar system. The Chinese imagery adds a new dimension, the possibility that its coma and tail structure might differ markedly from solar system comets, hinting at different volatiles, surface composition, or even formation environment. Spectroscopic studies published elsewhere already suggest unusual CO2-H2O ratios and atypical dust behavior. The added morphological insight from China's images could corroborate or challenge those findings. Meanwhile, the fact that Western telescopes are less active at this moment is not simply an operational footnote. It represents a vulnerability in our global observational network. Transient objects like 3I Atlas demand rapid, coordinated, multi-wavelength observation, optical, infrared, radar, spectrographic. If one major sector becomes unavailable, the mosaic of data becomes incomplete. The Chinese release, therefore, may serve as both a wake-up call and an opportunity to rethink collaborations, observation scheduling, data access, and contingency planning in the face of increasingly important interstellar visitors. On the astronomical front, the imagery raises some new puzzles. The asymmetries observed in the dust coma might suggest non-uniform surface activity, possibly driven by localized regions of volatile exposure. The tail's angle, brightness gradient, and dust grain distribution hint at complex interactions with solar radiation pressure, the solar wind, and perhaps the object's prior history of cosmic ray exposure or irradiation in interstellar space. That the Chinese data capture these phenomena at such a detail implies their instrumentation has reached the sensitivity and resolution threshold to discern grain-scale effects, or at least aggregate distributions, in an object millions of kilometers distant. This in turn invites questions. What does the dust size distribution tell us about the interstellar environment from which 3I Atlas came? Could the pattern of outgassing reflect a primordial surface layer preserved in deep space, now awakening as the sun's heat begins to act? Another implication lies in scientific prestige and strategy. The international competition to study rare and fleeting objects like 3I Atlas is intense. The Chinese release positions China as a serious player in deep space small body observation. This may trigger a recalibration of how observatories allocate time, how survey projects coordinate, and how nations invest in instrumentation and infrastructure. If Western facilities are perceived to be lagging or tied up in other priorities, then future interstellar object missions or surveys may pivot toward other partnerships. At the same time, the global science community may push for more open rapid data exchange to ensure that regardless of which country takes the lead on a given night, the findings propagate quickly, enabling parallel analysis. From a broader perspective, this episode illustrates the fragility and interconnectedness of observational science. Detecting, imaging, and characterizing an interstellar visitor demands not only advanced instruments, but also continuous vigilance, robust scheduling, and redundancy across geographic hemispheres and institutional frameworks. When one hemisphere or network goes dark, the risk of missing critical phases increases. The Chinese output thus becomes more than a data set. It becomes a strategic asset in a global observation strategy. For scientists watching the tail of 3I Atlas vanish into the deep sunlit background, every detail matters. The data-rich snapshot now made public should help refine dynamic models of the object's behavior, inform predictions of how its tail and coma will evolve, and help calibrate expectations about future interstellar visitors. The release also prompts reflection on the next frontier: push-capable survey telescopes, global networks of small robotic telescopes, space-based observatories dedicated to rapid detection and follow-up. The fact that China gained detailed images while Western networks struggled invites questions about whether our global system is optimized for transient interstellar phenomena. Perhaps more autonomous, real-time coordination across national boundaries is required. The Chinese images could thus act as a catalyst for proposals of truly global networks designed for interstellar object discovery and characterization. On the scientific front, the new imagery may feed into refinements of the object's trajectory, outgassing momentum changes, and dust ejection models. If asymmetric jets are confirmed, then models of non-gravitational acceleration may need adjustment, an important factor in predicting the object's path as it leaves the solar system. If dust grain size distribution and coma morphology diverge from expectations based on solar system comets, then theories of ice domain formation, irradiation history, or interstellar dust coating may be tested. The Chinese release may also prompt a reanalysis of earlier data from Western facilities. Previously observed anomalies now may make more sense in light of new structural detail. In essence, the snapshot provided by Chinese telescopes could serve as a Rosetta Stone for integrating disparate observational datasets across the world. In the realm of public perception and science diplomacy, the imagery and the timing create an unusual narrative. An interstellar visitor, already an exotic concept, is being imaged with unprecedented clarity, and at the same moment, parts of the global telescope network appear inactive. This irony is not lost on both scientific communicators and the public. The Chinese images become not only scientific data, but symbolic of shifting capabilities and astrophysical race dynamics. It invites reflection on how science is increasingly global, how observatories in all hemispheres must work in concert, and how no single nation can claim dominance in transient object science. As 3I Atlas carries on its brief but extraordinary visit, the legacy of this event may thus be as much about institutional change as about cometary science. If one considers the timeline, the Chinese release arrives at a turning point. 3I Atlas is moving closer to the sun. its activity expected to increase and evolve. The window for detailed study is narrowing. Any delay or gap in observation could mean missing phenomena like outbursts, fragmentation, or changes in tail morphology. That Chinese imagery arrives now is fortunate for the global science community, yet it also puts pressure on coordination. Combining these new images with spectroscopic data from infrared observatories, radar data from planetary missions, and visible photometry from ground-based telescopes becomes essential. The value of the Chinese images may multiply if integrated with complementary data. Conversely, the timing underscores that observational opportunism matters. When some telescopes go dark, the race for moments of opportunity tightens. Beyond pure science, the event may influence funding, collaboration, and instrument priorities. Agencies watching the success of one nation's observatory may decide to invest more heavily in their own capabilities or alter cooperation agreements. The notion that Western telescopes were underutilized or sidetracked when a major interstellar visitor came into reach raises uncomfortable questions about resource allocation, scheduling priorities, and readiness for the unexpected. Meanwhile, China's success may encourage further investment in deep space survey instruments, rapid response observatories, and space-based telescopes dedicated to interstellar visitors. This could in turn accelerate the entry of other nations into the field and alter the competitive landscape of astronomy. The imagery from China of 3Y Atlas also invites speculation about what more might be revealed. Could finer resolution or different wavelengths show fragments, jets, shields of dust, or previously unseen features? The presence of thermal anomalies, morphological complexity, or rapid changes in tail structure could hint at a nucleus that is unusually active or perhaps structurally weak. If the Chinese observatories continue to track the object as it moves outward, they might capture its fading tail and changes in coma more continuously than Western observatories currently appear positioned to do. In this sense, the release may only be the start, a prelude to a deeper campaign of observation that could reveal surprises as the object recedes. In sum, the release of the Chinese images of 3Y Atlas in the context of Western observatories being reduced in operation is far more than an isolated occurrence. It is a clear signal of shifting observational power, of the necessity for global coordination in the study of fleeting cosmic visitors, and of how even a single object can catalyze institutional and scientific change. 3. I-Atlas is not simply a comet or interstellar wanderer. It has become a test case for how humanity watches the heavens, how collaboration works or doesn't, and how prepared we are for the rare but deeply informative objects that drift into our solar system from the stars. The Chinese release of images of 3Y Atlas arrives at a moment when the Western observatory network appears to be stepping into shadow, either through maintenance, reduced coverage, or simply logistical constraints that have left key telescopes less active than ideal. In that gap, the Chinese data emerge not merely as incremental new pictures, but as a watershed. They reveal morphological detail, highlight the advantages of East Hemisphere and non-traditional assets, and force a re-examination of readiness and strategy for rare objects traversing our solar system. To begin with, the Chinese imaging campaign for 3Y Atlas demonstrates an agility and responsiveness that stands out. Many Western facilities operate with highly scheduled time, proposals submitted months in advance, and competing priorities such as large survey programs, planned instrumentation upgrades, or repairs. As a result, when a transient and rapidly evolving target like 3I Atlas arrives, the window for optimal imaging can slip away. Chinese observatories, in this case, appear to have mobilized quickly, allocated observation time, and processed data in a way that produced high-resolution results ahead of, or at least in the absence of, many Western facilities producing comparable outputs. The consequence is that the morphological state of the object at this epoch is being captured by China when other systems are less active, which means the Chinese data may fill a gap that would otherwise persist. The technical quality of the Chinese images is worth emphasizing. The coma of 3Y Atlas is shown with fine structure, bright sunward arcs or plumes, subtle asymmetries, and emerging tail features that suggest detailed dust motion and gas dynamics. Without quoting, one can observe that the data show more than a simple blurred blob. They show what appears to be directional ejection of material, non-uniform brightness, and tail morphology that varies with viewing geometry. That level of render allows scientists to model active areas on the nucleus, estimate dust grain size distributions, and compare the tail's angle relative to the anti-solar vector in ways that often require high signal-to-noise imagery. In effect, the Chinese images give a sharper snapshot of physical processes in play than many of the earlier wide survey captures from Western telescopes. The timing could not be more crucial. 3I Atlas is inbound, speeding toward perihelion, its activity expected to grow as solar heating increases. But the geometry of observation is changing. Phase angles, heliocentric distances, and Earth object separation are all shifting rapidly. In that context, every day of observation may show substantially different morphology. If the Western network is partly offline, or observing other targets, then the Chinese release may capture one of the few detailed before moments of activity. That means the global science community now has a base from which to compare subsequent images, including those that will come from Western telescopes when they resume full operations. It also means that if activity surges or fragments suddenly, the Chinese dataset becomes the reference baseline. Looking deeper, the implications extend into how observational networks are structured. Traditionally, Western observatories, whether in North America, Europe, or Australasia, have enjoyed primacy in high-end optical infrared astronomy. But the Chinese images of 3I Atlas serve as a reminder that geographical coverage, time allocation flexibility, data pipeline maturity, and willingness to pivot to opportunistic targets matter enormously for transient science. In the case of interstellar visitors, rare by definition, the ability to turn quickly and capture meaningful data while the object is still bright and accessible can define success. The fact that Chinese infrastructure managed to do so while Western systems were less active means the center of gravity in this kind of astronomy may be shifting. From a scientific perspective specific to 3Y Atlas, the Chinese images may reveal new phenomena. For example, the detection of structural jets or plumes suggests that the nucleus, whatever its size, is actively ejecting material not only radially away from the sun, but perhaps in localized eruptions. That would mean that the surface of 3I Atlas may contain heterogeneous volatile patches, fractures, or exposed ice regions rather than a uniformly sublimating surface. The tail morphology and its brightness gradient might be used to infer dust grain velocity distributions. Smaller grains will be blown away by radiation pressure more quickly, forming broader tails, whereas larger grains lag behind and produce narrower, longer trails. The Chinese data thus make possible deeper physical modeling. One can estimate how many grains of given size are being ejected, at what velocity, and infer properties of the surface or subsurface region from which they come. Another dimension is the interstellar origin of 3I Atlas and what these high-quality images can tell us about formation environments outside our solar system. If the images show dust grain color parameters, tail shape indicative of a particular dust mineralogy, or coma asymmetries reflecting volatile depletion, then one begins to test whether this object formed in conditions radically different from those in which solar system comets formed. The Chinese imaging helps close gaps in the dataset. Where Western observations might have lacked either resolution or time series, the Chinese data provide a more detailed epoch, enabling scientists to search for variations, before and after perihelion for example, that might indicate fragmentation, rotation changes, or even seasonal exposure of volatile patches. Crucially, the fact that Western telescopes are going dark for whatever operational reasons at this time may leave a void in continuous monitoring. In the study of active small bodies, especially interstellar ones, the continuousness of data is vital. Gaps in the observational record can mean missing key events. Outburst eruptions, fragmentation, momentary changes in tail orientation, or shifts in nucleus rotation due to jetting. When an object is passing quickly through our inner solar system, even a gap of days can translate into significant physical evolution. The Chinese data thus reduce the risk of data voids, but the reliance on a single geographical region also introduces risk. If weather, local instrumentation, or other logistical issues intervene, then the gap returns. The episode therefore underlines the importance of redundancy and diversity in the global observational network. In strategic terms, the event may alter how planetary science agencies plan their small body follow-up networks. Historically, large survey telescopes detect objects and high-end facilities perform follow-up. But 3I Atlas is a case where rapid response and detailed imaging matter more than long exposure surveys. The Chinese images demonstrate that high-resolution, responsive telescopes positioned appropriately can make a difference. Future planning may place greater emphasis on flexible scheduling, dedicated small-body follow-up arrays, global coordination east plus west plus space, and perhaps even the notion of rapid tasking instruments whose priority is opportunistic science rather than predetermined missions. If that becomes standard, then Western observatories that are tied to long surveys or massive instrumentation commitments may have to revise how they balance large-scale projects versus nimble targets of opportunity. Beyond infrastructure and strategy, the images deepen the intrigue of 3I Atlas itself. Each new observational gain forces fresh questions. What is the active fraction of its surface? How does the dust production rate compare to water or CO2 sublimation? The Chinese images, when paired with spectroscopic datasets from other resources, enable cross-comparison. For example, if dust jet directions align with spectroscopic hotspots of CO2 emission, then one can infer that the surface volatiles are being exposed in preferential zones. That in turn might link to the body's rotation axis, previous cosmic ray exposure history, or internal structure complexity. Without the detail delivered by the Chinese imaging, many of these questions would remain too vague for confident modeling. Another point concerns data sharing and scientific access. When one national network releases data at high resolution and others are less active, questions emerge about open data policy, coordination of worldwide observation, and rapid dissemination for community use. The Chinese images of 3Y Atlas could set a precedent: rapid release, broad access, and incorporation into global analyses. Conversely, if other observatories are inactive or hold data back, then science misses out. For interstellar object science in particular, where opportunities are fleeting, every data set has heightened value. The event may thus prompt new frameworks for international cooperation. Prearranged observation networks that automatically mobilize when an interstellar visitor is detected, agreements on data sharing, scheduling practices that allow dynamic follow-up, and perhaps standardized protocols for image release. The Chinese imagery also gives light to the concept of first-mover advantage in transient astronomy. Whoever images first, or with highest resolution, often sets the narrative and establishes the baseline from which subsequent observations are compared. In the case of 3I Atlas, Western telescopes may find themselves playing catch-up, interpreting Chinese imagery, aligning their own data onto those frames, and perhaps adjusting their expectations of what the object looks like. That dynamic can shift scientific perception. Observations become not just about catching up, but building upon a strong early lead. That may affect publication timing, data citation, and scientific recognition. The wider implication is that in transient astrophysics, flexibility and quick mobilization may matter as much as raw aperture size. On the observational science side, the Chinese images may reveal features that challenge existing comet models. For instance, if the tail is skewed or bifurcated, or if the coma appears clumpy, then one might infer that the nucleus is fragmenting, or has heterogeneous surface composition. If dust densities appear higher than expected for an object at its observed heliocentric distance, then one might ask whether 3I Atlas had undergone prior perihelion passages in its parent system, or whether interstellar exposure caused a different dust reservoir. The Chinese data might reveal subtle curvature in the tail caused by magnetic or solar wind interactions, dust charging, or anisotropic emission, features that would be difficult to interpret without high-resolution imaging. The fact that these features may be present makes the Chinese release truly significant. From a theoretical standpoint, 3I Atlas's characteristics, as revealed by the Chinese images, feed into questions of origin and evolution. For example, if the jets or plumes align with a particular axis, one might infer the spin state of the nucleus, the thermal lag of active regions, and perhaps the internal layering or fracturing. If the dust tail's curvature implies solar wind interaction rather than simple radiation pressure, then modeling must incorporate plasma dust interaction, which in turn might reflect an interstellar history of exposure. The result is that 3I Atlas becomes more than a curiosity. It becomes a physical laboratory for testing models of small body behavior in alien environments. The Chinese images provide the essential morphological context to drive that modeling. Consider also the pathway of 3I Atlas through the solar system. The Chinese images place the object in a specific geometry, inbound, nearing perihelion, at an epoch when activity is rising. That positional and morphological snapshot helps refine trajectory modeling, non-gravitational forces from outgassing jets, and expectations of future behavior. If the Chinese data show asymmetric jets pushing material preferentially in one direction, then that implies force vectors that must be included in orbital models. This is especially important for interstellar objects where the non-gravitational forces may differ from typical solar system comets due to different volatile inventories or structural integrity. Without such imagery, models could be under-constrained. The interplay between the Chinese imagery and the relative quiet of Western telescopes also prompts broader reflection on human investment in astronomy. The moment highlights that even well-funded observatories are vulnerable to scheduled maintenance, weather, instrumentation conflicts, or simply the pace of operations. It demonstrates that astronomy is not automatic. Telescope time must be earned, resourced, scheduled, and aligned with opportunity. The Chinese images essentially highlight that the observatory with the best session at the right time may be the one that secures the most impactful data. For future interstellar visitors, the global community may choose to adopt a rapid task protocol. When an ISO is detected, observatories share a rapid trigger network, time is freed, and observation campaigns mobilized. The Chinese example may serve as a proof of concept for such coordination. If one projects into the near future of this event without discussing aftermath, the Chinese images will likely become a benchmark dataset. Other observatories will align their measurements to the Chinese frames, comparing dust tail length, jet angles, coma brightness, surface brightness gradients, and more. Over time, as the object moves past perihelion and recedes, differences between images will yield insights into change. The fact that the Chinese imagery captures 3I Atlas in a more pristine state before peak solar heating means the dataset is especially valuable. It may show initial activity onset, give clues to how the object responded to solar insolation for the first time, and record the baseline before rapid evolution. The timing and quality thus combine to produce a dataset of high enduring value. There is also a subtle but important psychological and institutional aspect. The Chinese images reinforce that no single nation or network has exclusive dominion in astronomy. The fast-moving frontier in transient events, interstellar visitors included, rewards networks that are nimble, aligned across time zones, and backed by open data policies. For Western observatories, the fact that they appear less active in this critical moment may serve as a wake-up call. The prime target of discovery may not wait for your scheduling window, and readiness for opportunistic science may require rethinking resource allocation. In a field where serendipity plays a major role, the infrastructure must be both robust and flexible. The Chinese success could accelerate shifts in how time is allocated, how survey follow-up is handled, and how international collaboration is structured. The science of 3I Atlas itself also benefits from the Chinese images by giving more parameters for comparative analysis with the earlier interstellar objects, 1I Oumuamua and 2I/Borisov. With the Chinese morphological imagery, scientists can ask, how similar or different is 3I/Atlas's activity profile to those earlier cases? How does the dust coma morphology compare? Does the tail structure follow patterns seen in 2I/Borisov, or diverge? Are jets and plumes present in similar intensity? By providing a crisp morphological dataset earlier in the object's passage, the Chinese imagery raises the bar for comparative ISO science. We now have 3 cases, one of which has unusual imaging coverage that may unlock new patterns. That means theories about interstellar body origin, composition, and behavior can now test their predictions more rigorously. Consider the community of amateur and small telescope observers. The Chinese imagery may guide downstream observing. By providing high-resolution morphological context, amateurs and smaller observatories can point their equipment more effectively, tail direction, position angle of jets, etc. That means the Chinese data have a multiplier effect. They improve the efficiency of the broader observational network. Meanwhile, the gap in Western professional telescope coverage may be partially bridged by this cascade effect as the Chinese images inform global efforts. In that sense, the Chinese release plays an outsized role beyond their data alone. It is also worth reflecting on the discovery timeline and strategy for interstellar objects. 3. I-Atlas was detected, followed by rapid follow-up. But the Chinese images arriving at this juncture suggest that follow-up must not only be rapid but detailed and must cover morphological nuance. The event underscores that for interstellar visitors, the early phase of activity, prior to perihelion, may be more scientifically fertile than one might assume. If the Chinese images show early jets, dust bursts, or structural changes, then future observational campaigns might prioritize earlier epochs rather than just peak brightness phases. That could shift how proposals are prepared for future projects, what instrumentation is prioritized, and how observation windows are chosen. From a raw astrophysical angle, the Chinese images may also challenge expectations concerning erosion, fragmentation, and survival of interstellar objects. If the images show no fragmentation but substantial jetting, one might infer that 3Y Atlas has a structurally coherent nucleus despite its interstellar travel. Alternatively, if subtle fragmentation or outbursts are evident, then the object could differ markedly from solar system comets in structural integrity, indicating perhaps a longer exposure to cosmic ray bombardment or structural weakening in interstellar space. The Chinese images help frame those possibilities. Without them, speculation would be more open-ended. With them, modeling can incorporate more constraints. In many ways, the episode of Chinese imaging of 3I Atlas while Western observatories are less active may become a case study in observational astronomy. How network readiness, scheduling flexibility, global coverage, data calibration, and rapid dissemination combine to produce scientific advantage. It may drive a future era in which transient object science is treated as a global rapid response discipline rather than a secondary activity within large observatories. The latency between detection, follow-up, and high-resolution imaging may shrink further. The Chinese success may help shape that. If you like this video, please give it a like and subscribe to our channel. Also, leave your comments below and tell us. What are your thoughts on China releasing 3I Atlas images before Western telescopes went dark? We want to hear from you. Thank you for watching and see you next time.